A single piece of Egyptian granite holds a mirror to our modern world. Its surface is flawlessly smooth, its edges impossibly sharp, as if shaped by a machine. Yet this artifact is thousands of years old, created long before steel or electricity. This is the central mystery of the lost technology used to drill granite in ancient Egypt. By the end of this exploration, you will see the ancient world through a completely new lens, confronted by evidence that rewrites the story of human ingenuity. We will examine drill cores with spiral grooves that defy simple tools, and sarcophagi polished to a precision that seems to belong to another age. How could such advanced knowledge simply vanish from history? What does their silent stonework say about our own assumptions of progress? This silent witness is made of granite, a stone that speaks volumes through its very nature. To understand the depth of this mystery, we must first understand the material itself. Granite is not just any rock. It is a composite of different minerals, fused together under immense heat and pressure deep within the earth. The key ingredient here is quartz, a crystalline mineral that makes up a significant portion of granite's composition. On the Mohs scale of mineral hardness, a simple reference geologists use, quartz ranks a 7 out of 10. For perspective, the copper tools archaeologists have found in abundance from ancient Egypt rank around a 3. It is the difference between trying to carve wood with a hard piece of plastic and trying to carve that same wood with a diamond. The copper would simply wear away against the granite's quartz crystals, dulling long before it could make a meaningful cut. This is the Granite Conundrum in its simplest form. We have the evidence of the finished product, masterpieces of stonework, and we have the tools officially attributed to the culture that made them, and the two do not match. The evidence of this mismatch is not hidden. It is lying in plain sight, scattered across Egypt. In the quarries of Aswan, the unfinished obelisk remains attached to the bedrock, a colossal project abandoned. The tool marks on its surface tell a story of a method we can scarcely comprehend, with channels cut straight down into the living rock. In museum collections, you can find stone vessels, bowls, and jars carved from diorite and basalt, stones even harder than granite, with interiors so smoothly hollowed they feel like glass. And then there are the drilled cores. These are cylindrical pieces of granite, often found in ancient workshops, that were drilled out from larger blocks. They are perhaps the most telling pieces of evidence. Many of these cores display perfect, consistent spiral grooves running down their length, as if the drill bit sank into the stone with steady, unrelenting pressure. The spacing of these grooves is uniform, suggesting a feed rate, a mechanical precision that simple hand-powered tools struggle to explain. This is the technological gap. The artifacts demonstrate a capability, a level of craftsmanship that the traditional toolkit of copper chisels and stone hammers cannot logically achieve with such flawless, repeatable results. So if not those simple tools, then what were they using? The answer must be etched into the stone itself, waiting for us to learn its language. The most compelling evidence is not a grand monument, but a humble cylinder of stone. In the collection of the Petrie Museum in London rests a small, unassuming artifact, a drill core extracted from a deep hole in a block of granite. It was the renowned archaeologist Sir Flinders Petrie who first studied these cores in detail, and what he documented left him astounded. Running down the length of the core are perfect, consistent spiral grooves. These are not random scratches, but a precise record of a tool's motion, etched permanently into the granite. The grooves tell a clear story. Their uniform spacing indicates a steady, relentless feed rate, meaning the drill bit advanced into the impossibly hard stone at a constant speed. Modern engineers who have examined this, like researcher Christopher Dunn, point out that this feed rate is estimated in the realm of millimeters per revolution. This is a critical detail. To achieve such a consistent feed into granite with a hand-powered tool is extraordinarily difficult, akin to pushing a pencil into a block of wood at a perfectly even, slow speed without any variation in pressure or wobble. The ancient drill did not waver. It did not slow as it met the harder quartz crystals within the granite. It simply ate through the stone, removing material with a terrifying efficiency. The core itself is a negative space, the material that was removed, and its surface is so smooth, the grooves so mathematically regular, that it presents a powerful case. This is not the signature of a chisel being pounded and twisted by hand. This is the signature of a machining process. The core is a fossilized record, a single data point that whispers of gears, of leverage, of a tool applying immense focused power. And it is not alone. Similar cores have been found elsewhere, a repeating pattern in the archaeological record that says this was not an accident or a one-time wonder. This was their method, so we are left with a tangible object that contradicts our simplest explanations. If they were not using crude tools, then what kind of machine left this calling card in solid granite? But a single drill core is just a whisper. For the full chorus of this ancient technology, you must step inside the Great Pyramid and stand before the Sarcophagus of Khufu. This is no mere stone box. It is an 80-ton monolith of rose granite sitting in the heart of the pyramid's king's chamber. To simply move such a block from the quarry hundreds of miles away is a feat that strains imagination. But the true mystery is not its journey but its transformation. This colossal stone was hollowed out. Its interior was carved into a perfect, smooth chamber with corners that meet at precise 90-degree angles. The flatness of its surfaces is measured in fractions of a millimeter, a tolerance that feels industrial. Even more telling are the bore holes drilled into its sides, meant to hold a now missing lid. These holes are clean, cylindrical, and deep, echoing the same precision seen in the smaller drill cores. The logistical nightmare here is twofold. First, the sheer mass. How do you manipulate an 80-ton block to work on its interior? You cannot simply flip it over. Second, the precision. The tool marks that are visible on the unfinished outer surfaces show consistent parallel striations. These are not the chaotic, chipped patterns of a hammer and chisel. They are the signature of a cutting tool that moved in a fixed, straight path, removing material in even, controlled strokes. Think of the difference between whittling a piece of wood with a pocket knife and running that same wood through a table saw. One is freehand and variable. The other is guided, powerful, and repeatable. The sarcophagus suggests the latter. It represents a marriage of monumental scale and microscopic precision that should not exist in the age it is attributed to. This creates a profound puzzle for our historical timeline. Does the presence of such an object, locked within the world's most famous ancient monument, suggest its builders possessed a suite of technical knowledge we comfortably attribute to much later eras? The sarcophagus is not just a container, it is a statement. And to understand that statement, we must move from the artifacts they left behind to the tools that are conspicuously missing. These grooves and polished surfaces are more than just decoration. They are a direct transcript of the manufacturing process, a language of force and motion written in stone. To understand the lost technology, we must learn to read this language. Every mark tells a story. The continuous, helical striations spiraling down a drill core, for instance, are a clear record of a rotating tool. The spacing of these grooves, their depth and consistency, speaks of a feed rate and a cutting force that remained constant, even as the drill met harder and softer pockets of mineral within the granite. This is not the erratic, chipped pattern of a handheld tool being struck. It is the smooth, predictable signature of a machine under power. Then there are the flat, sawn surfaces, like those found on the sides of sarcophagi or the base blocks of temples. These expanses of stone are often polished to a mirror finish, but under magnification they reveal another tale. Fine, parallel striations run across them. These are the marks left by a cutting blade, likely an abrasive slurry of sand and water, being drawn back and forth across the stone's surface with immense, sustained pressure. The consistency of these lines suggests a guided motion, a saw blade that did not wander. Perhaps most telling are the intricate internal corners, like the perfect 90-degree angles inside a granite box or vessel. Creating a sharp internal corner in any material is a challenge. With a chisel, you would expect rounding, chipping, or a series of overlapping strikes. Yet many Egyptian artifacts feature crisp, clean interior angles. This suggests the use of a boring technique, where a tool could cut precisely into a corner and remove material without fracturing the surrounding stone. It implies a tool that could apply focused force in a very specific, controlled way. When researchers compare these ancient marks to those made by modern machinery, the similarities are startling. The helical grooves on a granite core from Giza bear a striking resemblance to those produced by a modern diamond-tipped drill, where a rigid shaft rotates at high speed under significant downward pressure. The parallel striations on a sawn surface look identical to marks left by a modern wire saw, a loop of cable coated in diamond abrasive that slices through stone like butter. The physics of cutting granite have not changed. The stone responds to force and abrasion the same way today as it did 4,000 years ago. Therefore, the marks left behind are a reliable guide. They testify to a process that involved two things the traditional copper and dolerite tool kit lacks: immense sustained pressure and a rapid, repetitive cutting motion. The stone is our primary witness, and its testimony points unequivocally toward a level of mechanical sophistication we are only beginning to appreciate. If we accept this testimony, the next logical question becomes unavoidable. What kind of power source could have driven such machines? The official explanation for this stonework is one we all recognize. Mainstream archaeology points to a toolkit of copper chisels, stone hammers, and simple abrasives. The process, as described, is one of immense patience and manpower. Workers would have used hard dolerite stone balls to pound along a desired line on the granite, literally pulverizing the crystalline structure grain by grain. For finer work and cutting, a slurry of wet sand, an abrasive harder than copper, would be used with a copper saw. The theory suggests the copper blade, itself soft, would drag the sharp quartz sand particles across the granite surface, allowing the sand to do the cutting in a slow, grinding fashion. On the surface, it sounds plausible, a testament to human perseverance, and for softer stones like limestone, these methods are demonstrably effective. But when we apply this theory to the hard granite artifacts, the story begins to unravel under practical scrutiny. The first issue is the material itself. Copper is a soft metal. When a copper chisel is struck against granite, which is filled with quartz crystals harder than steel, the copper edge mushrooms and deforms. It dulls almost immediately. Laboratory tests have shown that a copper tool would need constant resharpening and would be consumed by the work at an astonishing rate, long before it made significant progress into the stone. The second issue is scale and logistics. Consider the Serapeum of Saqqara with its dozens of massive granite sarcophagi, each weighing over 70 tons. To hollow out just one of these using a copper saw and sand abrasive becomes a problem of almost comic proportions. Researchers have calculated the staggering quantities involved. To achieve the deep, smooth-cut scene, it would require miles of copper saw blade, worn away and replaced continuously, and tons upon tons of precisely graded sand, constantly flushed through the cut. The workshop waste alone would be a mountain, yet no archaeological site has revealed evidence of this scale of industrial consumption for these materials. There is a profound disconnect here, a credibility gap between the proposed method and the polished perfection of the result. The Orthodox Toolkit struggles to explain the precision, the speed implied by the feed rates in the drill cores, and the sheer volume of work completed. It is like suggesting a community built a modern highway using only spoons and baskets of gravel. The determination is admirable, but the physics and the logistics simply do not align with the evidence left behind in the stone. This gap is not a criticism of the ancient artisans, but rather of our modern understanding. It forces a difficult but essential question. If the tools we have found are not the ones that created the most challenging artifacts, then what are we missing? The persistent hum of copper against granite would have been deafening, a sound of pure futility. This is where the abrasive theory steps in, offering a clever workaround to the hardness problem. The idea is simple, and in principle it works. If you cannot cut the stone with your tool, you must make the stone cut itself. The method involves a simple copper tube, perhaps flanged at the end, mounted on a wooden spindle. Instead of relying on the soft copper to bite into the granite, workers would pour a wet slurry of quartz sand and water into the cutting area. The copper tube is then rotated back and forth or spun continuously. The key is the abrasive. Quartz sand, the same mineral that makes granite so hard, is now the cutting agent. The sharp, angular sand grains become embedded in the soft copper edge, and as the tube rotates, these countless tiny particles act like microscopic teeth, grinding and scratching away at the granite surface. With enough water to flush away the powdered debris and constant renewal of the abrasive slurry, the tube would slowly, inexorably, eat its way down into the stone, leaving behind a cylindrical core. In demonstrations, this method does indeed produce a hole. It proves that with simple materials, the ancient Egyptians possessed the fundamental knowledge to work hard stone. But when we hold this theory up against the specific evidence, particularly the drill cores studied by Petrie, the fit is not perfect. The process is brutally slow and requires immense, sustained manual torque to keep the drill turning under pressure. The slurry is a chaotic medium, with sand grains of random sizes and shapes tumbling and crushing in the cut. This randomness should produce a rough, irregular surface on the core, a surface scarred by the unpredictable grinding of countless particles. Yet the Petrie cores show something entirely different. They display fine, consistent, parallel spiral grooves. These are not the marks of a chaotic abrasive grind. They are the signature of a single, continuous cutting point, or a series of precisely arranged points, moving in a fixed rotation. An abrasive slurry cannot explain this level of order. Furthermore, the calculated feed rate, the steady speed at which the drill advanced, is extraordinarily high for a manual, abrasive process. To achieve that feed, workers would have had to apply not only tremendous rotational force, but also perfectly consistent downward pressure for hours on end, without the drill wobbling or the slurry clogging. The theory demands almost unimaginable time and labor for each and every hole, a scale of effort that seems at odds with the sheer number of precisely drilled holes found across Egypt. The artifacts whisper of efficiency and speed, while the abrasive method, as we understand it, speaks only of immense grinding patience. This leaves us with a fascinating paradox. The abrasive theory is correct in its basic premise, but perhaps incomplete in its ingredients. What if the abrasive was not simple, random beach sand? What if it was something harder, something more consistent, something that could be fixed to a cutting tool to create those clean, mechanical grooves? The search for the lost technology may not be for a complex machine, but for a forgotten material, a secret ingredient that turned a simple copper tube into a precision drill bit. Perhaps the secret was not in the machine, but in the material itself. What if the ancient Egyptians possessed a cutting agent so effective, so durable, that it transformed a simple copper tube into a tool capable of carving history into granite. This leads us to a compelling hypothesis, one that ventures into the realm of lost material science. The idea is not that they had complex engines, but that they might have mastered a superior abrasive, a substance far harder than the quartz sand we assume they used. The most famous candidate, of course, is diamond. Diamond is the hardest natural material known, ranking a perfect 10 on that same hardness scale where quartz is a 7. Even tiny, fragmented diamond crystals, embedded into the edge of a soft copper drill, would act like microscopic, indestructible teeth. They would not crush and wear away like sand, but would maintain a sharp, consistent cutting edge, potentially creating those clean, parallel grooves we see on the drill cores. While no ancient Egyptian diamond-tipped tools have ever been discovered in an archaeological dig, we must remember that absence of evidence is not evidence of absence, especially for something as small and consumable as abrasive grit. We know the Egyptians were master traders, connected to networks that stretched deep into Africa and possibly to India, regions known for diamond sources. It is not impossible that they prized these brilliant stones not for jewelry, but for their practical, industrial power. A more likely and historically documented material is corundum. This mineral family includes rubies and sapphires, but its more common form is a dull, incredibly hard gray stone known as emery. Emery is a natural mixture of corundum and other minerals, and it has been used as an abrasive for millennia. Ancient texts from other cultures reference its use for polishing and carving. If the Egyptians were using a carefully selected, crushed emery powder of a consistent grain size, mixed into a precise slurry, the cutting efficiency would leap exponentially compared to ordinary sand. The process would still be manual, requiring immense labor to turn the drill, but the results would begin to align with the evidence. The feed rate could be higher, the grooves cleaner, and the overall time required dramatically reduced. This idea of a lost abrasive chemistry is a powerful bridge. It does not require us to invent fantastical machines. Instead, it asks us to reconsider the sophistication of their everyday knowledge. What if their workshop recipes, passed down orally from master to apprentice, contained formulas for abrasive slurries of specific consistencies, formulas that were lost when their civilization faded or their stoneworking traditions ended? This is a knowledge gap, not just a tool gap. It suggests they understood materials on a granular level we have not credited them with. They may have known that to conquer the stone, they needed to harness a piece of the stone's own crystalline family, a harder sibling, to do the work. This pursuit of the perfect cut leads us inevitably to the next logical step. If they had such advanced material knowledge, would they have been content with only human muscle to apply it? Or would the sheer ambition of their projects have pushed them to seek a source of power beyond the limits of the human arm? Human muscle has its limits, a fact the pyramid builders would have known intimately. Yet the stone itself seems to tell a different story, one of power and precision that pushes far beyond the capacity of the human arm. This brings us to the most controversial interpretation of all, a theory that suggests the ancient Egyptians did not just have better abrasives, but better machines. Researchers like Christopher Dunn, an engineer who has studied the artifacts firsthand, propose that the tool marks are not just similar to modern machining, they are identical to it. They argue that the evidence points toward processes like ultrasonic machining or the use of diamond-tipped fixed-point drill heads. To understand this, we must look at how we cut hard, brittle materials today. Ultrasonic machining is a modern technique used for precisely cutting materials like advanced ceramics or glass. It works by vibrating a tool tip at an extremely high frequency, tens of thousands of times per second. This ultrasonic vibration causes the abrasive slurry in the cut to hammer the surface of the material at a microscopic level, fracturing it away in tiny, controlled particles. The result is an incredibly smooth, precise cut with no thermal damage, and it can create those clean, sharp internal corners that baffle us in granite boxes. The parallel striations on a sawn surface could be the mark of a blade vibrating at such a frequency, guided with unerring straightness. A fixed-point drill, one with actual cutting teeth made of something like diamond, would also explain the perfect helical grooves on a core. A rotating drill bit with embedded diamond crystals would act like a modern core drill, slicing through the quartz in granite rather than just grinding it. The machine required for this, however, is not simple. It demands a rigid spindle to prevent wobble, a significant and constant source of power to maintain rotation under heavy load, and a feed mechanism to advance the drill at that steady, relentless rate. The calculated feed rate seen on some cores, estimated at roughly 1/10 of an inch per revolution, is not just a number. To an engineer, it is a specification. It dictates the required torque, the horsepower, the structural integrity of the entire apparatus. It implies a machine of substantial weight and stability. So where does the power come from? The theory does not necessarily invoke electricity. It could be hydraulic, using water pressure from the Nile channeled through clever systems. It could be mechanical, using large capstans turned by teams of workers or animals to generate rotational force through complex gearing, storing that energy in a heavy flywheel to ensure smooth, uninterrupted motion. The core of this idea is not about finding a forgotten power cord, but about recognizing a possible sophistication in mechanical engineering that we have not attributed to that era. This line of inquiry directly challenges our accepted timeline of human progress. We have a narrative that says the Industrial Revolution, with its precise machinery, began in the 18th century. But what if the principles of precision engineering were discovered, applied on a monumental scale, and then lost not once but perhaps several times throughout history? The artifacts sit before us asking a difficult question. If we strictly interpret the physical evidence they present, ignoring for a moment all our assumptions about the past, what is the simplest explanation? 1,000 men grinding sand for a lifetime, or a master artisan guiding a powerful, purpose-built machine for a week? The answer we lean toward says more about our view of history than it does about the stones themselves. The silent testimony of a single sarcophagus is one thing, but an entire underground gallery of them is a declaration. To grasp the true scope of this lost technology, you must leave the soaring pyramids behind and descend into the earth at Saqqara, into the shadowed halls of the Serapeum. Here, in this subterranean labyrinth, you are not confronted by a singular masterpiece, but by an assembly line of mysteries. Dozens of colossal boxes, carved from single blocks of rose granite and black diorite, rest in niches along long, torch-lit corridors. Each one is a monolith weighing up to 100 tons, the equivalent of a full-grown blue whale carved from solid stone. Their presence here, deep underground, is the first impossible logistical puzzle. But it is their condition that truly defies belief. The surfaces of these sarcophagi are not merely smooth, they are engineered. Measurements reveal that the flat tops and sides are parallel to within a few thousandths of an inch over their entire length, a tolerance we associate with modern machine shops, not ancient crypts. The corners meet at perfect 90-degree angles, sharp and precise. The fitted lids, many weighing over 15 tons themselves, were designed to sit with such airtight precision that a thin sheet of paper cannot be slid between the lid and the box. This is not decorative artistry, it is precision engineering on a monumental scale. The sheer repetition is the most telling clue of all. This is not a one-off achievement, a lucky strike by a team of genius artisans. This is a standardized product. Box after box exhibits the same flawless finish, the same exacting specifications. This points to a mastered, repeatable process, a technology that had been refined and systematized. It was an industry. Think of it not as a sculptor's studio, but as a factory floor buried beneath the sand. Every logistical question we asked about the single sarcophagus in the Great Pyramid is amplified here 100-fold. How were these 100-ton blocks transported from distant quarries down narrow ramps and maneuvered into perfect alignment in these cramped underground chambers? Once in place, how were they worked on? The ceilings are low, leaving no room for large teams to swing heavy tools. How do you achieve a mirror polish on a surface 20 feet long when you cannot even stand back to see your work? The Serapeum removes all possibility of explaining these feats as accidental or born from brute force. It presents not a solitary anomaly to be explained away, but an entire warehouse of them, a silent, overwhelming body of evidence. This place stands as the ultimate case study, proving that the builders operated with a level of technical certainty we are still struggling to comprehend. The polished boxes of the Serapeum ask a question that echoes far beyond their stone walls. If this level of engineering was possible, when did it truly begin? To find an answer, we must look not at the artifacts themselves, but at the ground they stand upon. Geologist Robert Schoch introduced a startling perspective by examining not the Sphinx artistry, but its weathering. He observed deep, vertical fissures and undulating erosion patterns on the limestone body of the monument, patterns that he argued were not caused by wind and sand, but by prolonged, heavy rainfall. This type of weathering points to a climate that has not existed in Egypt for thousands of years, specifically to a time before the Sahara became a desert. If correct, this suggests the Sphinx, and perhaps the core structures around it, could be vastly older than the dynastic timeline of 2500 BCE. This is not a small adjustment. It is a seismic shift in chronology, pushing the origins of these sites back into a prehistoric epoch, perhaps as far back as 7,000 or even 10,000 years ago. Suddenly, the context for the advanced granite work changes entirely. It is no longer a product of the known Egyptian kingdom, but potentially a relic from a time so distant it exists only in geological memory. This revised timeline forces us to reconsider everything. If the Sphinx and the megalithic core of Giza are remnants of a much older culture, then who were they? What kind of world did they inhabit? This is where the mystery expands from a question of tools to a question of civilization itself. The idea of a precursor culture, a forgotten chapter in human history, emerges from the shadows. Perhaps the dynastic Egyptians we know so well were not the original builders, but the inheritors. They found these colossal, weathered monuments already ancient on the landscape, incorporated them into their own religion and mythology, and perhaps even tried to replicate the techniques with varying degrees of success. This perspective frames the impossible granite technology not as an isolated, miraculous achievement of a single culture, but as the surviving signature of a much broader and now lost technological age. Imagine a scenario where the knowledge to work stone with such precision was developed over millennia by a sophisticated society, only to be fragmented and nearly erased by a cataclysmic climate shift, like the dramatic desertification of North Africa. The technology did not vanish overnight because of a single war or disaster, but faded over generations as the environment changed, populations migrated, and the urgent need for survival replaced the grand ambition of monument building. The core techniques, the recipes for abrasives, the designs for machines could have become legend, then myth, and finally been forgotten. When we view the drill cores and sarcophagi through this lens, they transform from impressive artifacts into tragic fragments. They are the scattered pieces of a much larger puzzle, a puzzle for which we have lost the box-top picture. This broader mystery does not provide easy answers for how they drilled granite, but it provides a crucial framework for why our conventional explanations feel so inadequate. It suggests we are not just looking for a missing tool, but for a missing epoch of human ingenuity. The stones were shaped not at the dawn of recorded history, but perhaps at the twilight of a world we can no longer see. The granite itself might hold the answer in a frequency we can no longer hear. Beyond gears and abrasives lies a more ethereal possibility, a technology not of matter but of vibration. Ancient texts from diverse cultures, from the Vedas of India to legends of the builders of Stonehenge, whisper of a common thread, stones that were moved, shaped, or made weightless by the power of sound. Could these stories be a fragmented memory of a real, lost science? Modern physics shows us that acoustic resonance is a formidable force. Every object has a natural resonant frequency, a specific pitch at which it vibrates most easily. When sound waves at that exact frequency are applied with enough intensity, remarkable things happen. We've all seen the classic demonstration where an opera singer shatters a wine glass with a sustained, pure note. The sound waves transfer energy into the glass, amplifying its natural vibrations until the material structure fails. Now, apply that principle not to break, but to manipulate. Researchers in fields like materials science have demonstrated that high-intensity, focused sound can affect the properties of substances, temporarily reducing friction or creating standing wave patterns that can suspend small objects in mid-air, a phenomenon known as acoustic levitation. This is not magic, it is physics operating at an extreme. The speculative leap for ancient technology is this. What if the builders discovered the resonant frequency of granite? What if, by using massive tuning forks, specially shaped chambers, or choruses of voices chanting precise tones, they could generate a sound field that caused the stone to vibrate internally? This sustained vibration could have several profound effects. At a certain intensity, it might temporarily reduce the stone's effective hardness, making it more pliable, almost like a stiff putty, allowing tools to work it with far less effort. This concept, sometimes called sonic drilling, is used today in advanced machining. More intriguingly, if the frequency and amplitude were perfectly tuned, it could create a cushion of vibrating air between the stone and the ground, dramatically reducing friction. A 100-ton block that would normally require the labor of hundreds to drag on sledges might, under the influence of this sonic field, become movable by a small team. This theory is compelling precisely because it leaves no conventional evidence behind. No strange machines would be found in the ruins, only perhaps peculiar acoustic chambers or instruments. The tool marks on the stone would be made by ordinary tools, but the reason those tools were effective would be the invisible, sonic key that unlocked the granite's resistance. It suggests a holistic understanding of the world where science, spirituality, and practical application were not separate disciplines, but intertwined aspects of a single knowledge. The chant of a priest, the note from a horn, might not have been mere ritual, but the activation code for a physical process. While firmly in the realm of speculation, this idea forces us to expand our search beyond the tangible. If they mastered such a principle, their greatest tool was not made of copper or stone, but of air itself, shaped by wisdom into a force that could move mountains. Machines, however advanced, do not build themselves. The true scale of this ancient mystery becomes clear not when we look at a single drill core, but when we consider the army required to wield it. Even if we grant the existence of these sophisticated tools, their deployment on a project like the Great Pyramid represents a logistical triumph that rivals the engineering. This was an operation of breathtaking complexity, a symphony of human coordination that had to sustain itself for decades. The workforce was not a faceless mob of slaves, as outdated stories suggest, but likely a rotating core of highly skilled laborers, artisans, and engineers, supported by a vast, invisible network. Think of the supply chain alone. For a workforce estimated in the tens of thousands, you need not just tools, but food, water, shelter, and medical care delivered daily to a remote desert plateau. This implies bakeries the size of factories, herds of cattle managed on an industrial scale, and a constant shuttle of boats on the Nile bringing supplies from estates across Egypt. The organization required is almost military in its precision. This points to a society with an advanced understanding of project management, of resource allocation, and of human capability. It was a civilization that could plan in generations, not just seasons. Within this machine, the stoneworkers themselves were the most crucial component. Evidence from worker settlements near Giza suggests they were not slaves, but valued specialists. They were divided into crews with names like the Friends of Khufu or the Drunkards of Menkaure, hints of a proud, guild-like structure. These were not men swinging hammers at random. They were likely master craftsmen who spent lifetimes honing a specific skill, perhaps operating a specific type of drill or saw. The knowledge of how to mix the perfect abrasive slurry, the exact tension for a cutting wire, the resonant frequency for a specific stone, this would have been proprietary information passed from master to apprentice in guarded workshops. This compartmentalization is key. It means the full technological system was not held in one mind, but distributed across an entire ecosystem of experts. A master driller might know everything about his tool's operation, but nothing of how the abrasive was formulated. The abrasive maker might not understand the logistics that brought his raw materials from a distant mine. This is how sophisticated systems protect themselves, by distributing the keys, but it is also how they can be utterly lost. If a social disruption, a climate shift, or an economic collapse scatters these guilds and breaks their chains of apprenticeship, the knowledge shatters into fragments. The tools might remain, but the living context to use them effectively evaporates. The organizational genius behind the pyramids, therefore, may be the greatest technology of all. It was the operating system that allowed the hardware to function. Losing a drill is a setback. Losing the guild structure, the supply networks, and the generational patience to execute a 20-year project, that is a catastrophe from which a culture may never fully recover. This systemic view forces a humbling realization. We may be searching for a lost object, when what was truly lost was an entire world of coordinated thought. Granite was not chosen for its convenience, but for its soul. To grasp the immense effort behind these artifacts, we must step into the ancient Egyptian mind, where the material world and the spiritual realm were deeply intertwined. Their cosmology saw the universe as an ongoing struggle against chaos, a need to create islands of perfect, eternal order. Granite, with its fiery volcanic origins and incredible durability, was the ultimate embodiment of this order. It was the stone of eternity. This symbolism is rooted in one of their most sacred objects, the Benben stone. This was a pyramidal stone, likely meteoric iron or a hard stone, venerated in the temple of the sun god Ra at Heliopolis. It was seen as the primordial mound, the first solid land to emerge from the watery chaos at the dawn of creation. Over time, the pyramidal shape and the idea of a capstone made from an indestructible material became directly linked to the pyramids themselves and the sarcophagi placed within them. To house a pharaoh's ka, his eternal spiritual essence, within a box of granite was to replicate that first act of creation. It was to place him upon a new Benben, securing his rebirth and his journey into the afterlife within a microcosm of perfect, unchanging stability. The hardness of the stone was not an engineering hurdle to be minimized. It was the very quality that made it sacred. A softer stone like limestone might erode over centuries, but granite promised to defy time itself. This transforms our understanding of the work. The relentless pursuit of a mirror finish, the obsession with perfect angles and seamless lids, was not merely a display of skill. It was a ritual act. Every stroke of the saw, every revolution of the drill was an act of devotion, a physical prayer to create a vessel so flawless that not even a hair's breadth of chaos could enter. The spiritual imperative demanded technical perfection. This cultural need becomes the missing catalyst in our search for the lost technology. When your society's most profound goal is to create an eternal, indestructible home for a god-king spirit, you do not settle for good enough. You innovate, you experiment for generations, you pour resources into solving the impossible because the stakes are not just practical, they are cosmic. The master craftsmen were not just laborers, they were priests of precision, mediating between the human world and the divine through their command of stone. Their workshops were temples of applied physics. This perspective helps resolve a lingering paradox. If the technology was so advanced, why was it seemingly abandoned or forgotten after the Pyramid Age? The answer may lie in the fading of the specific religious and cultural fire that demanded its use. As dynasties changed and theological focuses shifted, the overwhelming drive to create these specific, perfect granite vessels for the afterlife may have diminished. The knowledge so tightly held within specialized guilds and fueled by a singular purpose could have atrophied without that constant, monumental demand. The technology did not vanish because it failed, but perhaps because the world-changing need for it slowly passed into history. But the echoes of this ancient craft are not confined to the sands of Egypt. Across oceans and continents, in landscapes as diverse as the high Andes and the jungles of India, other stones tell a similar story. This forces us to ask a pivotal question: was Egypt truly unique, or were its artisans part of a wider, perhaps even shared, tradition of lost precision? To find out, we must journey to the windswept plateau of Pumapunku in Bolivia. Here, the stonework defies simple explanation. Enormous blocks of andesite, a stone as hard as granite, are cut with a geometric madness. You will find H-shaped blocks with perfectly parallel grooves, stone slabs with rows of identical, drill-like holes spaced with machined regularity, and interlocking pieces with complex, recessed channels that fit together with uncanny accuracy. The precision is not in grand, smooth surfaces, but in the intricate, modular assembly of components that look less like architecture and more like parts of a colossal, prehistoric machine. The scale is smaller than the pyramids, but the technical signature is just as baffling. Then shift your gaze to southern India, to the shore temples of Mahabalipuram. Here, artisans did not build with blocks, they subtracted them. Entire temples, complete with intricate pillars, sculpted deities, and vaulted ceilings, were carved downward from single, colossal outcroppings of granite. This is the art of monolithic sculpture on a breathtaking scale, demonstrating an intimate, fearless mastery over the stone. They shaped it as a potter shapes clay, but their medium was a mountain. While the styles are culturally distinct, the underlying message in the stone is similar. A demonstration of control over hard material that seems to leapfrog expected technological steps. These global parallels present us with two profound possibilities. The first is the tantalizing idea of a shared, archaic technological tradition, a forgotten school of knowledge that spanned the ancient world. Could there have been a common source, a primordial civilization, or a network of seafaring engineers whose techniques influenced builders from the Nile to the Andes? It is a theory that lives on the fringe of history, fueled by the eerie similarity of certain megalithic styles. The second, and perhaps more challenging possibility, is one of independent convergence. This suggests that human ingenuity, when driven by powerful cultural or spiritual motivations and faced with the same immutable laws of physics, can arrive at startlingly similar sophisticated solutions, even across vast distances and without contact. It is the principle that two isolated cultures, both needing to move a 100-ton block, might independently invent the lever, the sled, and the ramp. But does this principle fully explain the specific precision, the machine-like tolerances we see? That is the heart of the debate. This global perspective is crucial, for it prevents us from placing ancient Egypt in a vacuum of wonder. It frames their achievement not as a solitary miracle, but as perhaps the most well-preserved and grandest example of a deeper pattern in human history. It suggests the mystery of the granite drill is not an Egyptian mystery alone, but a human one. The stones of Puma Punku and Mahabalipuram are not answers, but they are powerful, echoing questions carved in rock, asking us to reconsider the entire map of our technological past. Theories and legends are one thing, but stone does not lie. To truly test our understanding, we must move from speculation to experiment, to see if our proposed tools can actually create the evidence left behind. In recent decades, teams of skilled engineers and archaeologists have done exactly that, attempting to replicate the ancient granite work using only the materials we believe were available. They gather copper tubing, dolerite pounders, quartz sand, and water, following the orthodox methods to the letter. The process begins with patience and optimism. A copper tube is mounted on a simple wooden spindle. A slurry of sand and water is poured into a starting groove on a granite block, and teams of people take turns rotating the drill back and forth, applying steady downward pressure. At first, it works. A fine powder, the pulverized granite, begins to wash out with the slurry. A hole is slowly, undeniably being formed. This is the proof often cited, the demonstration that the method is possible. But as the hours stretch into days, the reality of the experiment becomes painfully clear. The progress is agonizingly slow, measured in fractions of an inch per hour. The soft copper tube wears away at an alarming rate, requiring constant replacement or reshaping. The sand abrasive, crucial to the cutting, is itself being crushed into useless dust within the cut, losing its sharp edges and requiring constant replenishment. The manpower required is immense, not for a short burst, but for a sustained, grueling effort just to produce a single, shallow hole. And then comes the moment of truth, when the experimental core is finally extracted and compared to an ancient one like the Petrie core. The difference is stark. The modern core, created with a chaotic abrasive slurry, shows a rough, pitted surface. The grinding of countless random sand grains has scarred it with an irregular, matte texture. There are no fine, parallel spiral grooves, only a general unevenness. The ancient core, by contrast, gleams with a kind of mechanical clarity. Its surface is smoother, and those telltale helical grooves are crisp and uniform, a record of a clean, continuous cutting action. This empirical gap is the most powerful evidence we have. The experiments show us what is achievable with the toolkit we have attributed to the ancients, and they demonstrate its profound limitations. They prove that with immense time and labor, you can make a hole in granite, but they also prove that this method does not produce the specific, precision marks we actually find on the artifacts. It is like proving you can write a novel by carving each letter individually into a slab of wood with a nail. Yes, it can be done, but the time required and the quality of the script would be entirely different from one written quickly with a pen. These modern attempts are not failures, they are revelations. They empirically demonstrate a discrepancy. They show that while the basic abrasive principle is sound, the ancient results imply an efficiency, a control, and a consistency that the simple sand and copper model cannot deliver on its own. The experiments do not tell us what the lost technology was, but they shout with the authority of tested physics that our standard model is incomplete. Something is missing from the recipe, a variable that turns a laborious, crude process into one of startling precision. This leaves us standing before the artifacts with a new respect, forced to acknowledge that their creators possessed a practical secret we have yet to fully rediscover. The flawless surfaces of the granite boxes are a testament to a mind that could think in perfect planes and absolute angles. This level of precision engineering could not have been achieved by skilled hands alone. It required a foundation of equally precise thought, a sophisticated language of mathematics and geometry that guided every cut. The evidence is not written on papyrus but encoded in the stone itself. The perfect right angles, the mirror-flat surfaces, the consistent proportions repeated across different monuments, all whisper of a master plan, a set of intellectual tools as advanced as any physical drill. This raises a profound possibility that the true lost technology of ancient Egypt is not a machine, but a system of knowledge. The artisans may have used a form of applied geometry so intuitive and advanced it has escaped our modern interpretation. Consider the simple act of ensuring a surface is perfectly flat over a distance of 20 feet. Without a modern straight edge or laser level, how is it done? One method involves the use of water. A shallow, level trough of water creates a perfectly flat reflective surface, a natural horizon line, by sighting across it or using it to calibrate a simple wooden frame. A master could transfer that perfect plane onto stone. For right angles, the geometric principle of the 3-4-5 triangle, a cornerstone of the Pythagorean theorem, creates a perfect 90-degree corner. A chord knotted in the ratio of 3 units, 4 units, and 5 units when stretched tight will always form a right angle. This knowledge is timeless and tool-independent. The staggering accuracy of the pyramid's base, with its sides aligned to the cardinal directions within a fraction of a degree, suggests another layer of celestial geometry. This was not guesswork. It implies a method of astronomical observation so precise they could fix true north using the rotation of the stars, and then translate that cosmic alignment onto the desert floor with breathtaking accuracy. This points toward a lost metrology, a system of measurement. Did they use a standard unit based on something universal, like the circumference of the Earth or the vibrations of a specific frequency? Some researchers propose the pyramid builders used a royal cubit that was not a random length, but a fraction of the planet's polar radius, embedding a scale of the world into their architecture. Whether this is true or not, the consistency of their work demands a reliable and shared standard, a ruler everyone on a continent-spanning project could trust. Then there are the harmonic proportions. The dimensions of chambers, the angles of passages, often relate to each other through ratios like pi or the golden mean. Were these simply happy accidents of a convenient building scale, or were they intentional, reflecting a belief that sacred spaces should resonate with the mathematical harmony they perceived in the cosmos? The use of templates is almost certain for repeating complex shapes. A master pattern, perhaps made of wood or hardened clay, could be used to transfer a perfect curve or a specific angle onto granite again and again, ensuring standardization. This moves the mystery from the workshop floor to the drafting room. The master planners were not just foremen, they were geometers, astronomers, and philosophers. Their greatest tool may have been a diagram drawn in sand, a set of proportions chanted like a mantra, or an alignment ritual performed under the stars. This conceptual framework turned an ambitious construction project into an act of world-making, aligning stone with sky and measure with meaning. If this knowledge was orally transmitted within secretive priestly guilds, its loss would be as complete as the loss of any physical machine. We can see the magnificent output, the equations solved in stone, but the elegant working out of the problem, the graceful logic that made it all possible, has faded into silence. The disappearance of such profound knowledge is perhaps the most haunting part of this entire mystery. How does a civilization's mastery over stone, a technology capable of shaping the very bones of the earth, simply fade into silence? To lose a tool is one thing, but to lose the understanding of how to make it, how to use it, and why it worked, is a loss of an entirely different magnitude. This vanishing act forces us to consider the fragile nature of knowledge itself, especially when it is held not by machines, but by human minds and hands. History is not a straight line of progress. It is a story punctuated by periods of astonishing regression where advanced techniques are forgotten for centuries. Consider the secret of Roman concrete, a recipe that produced a marine mortar so durable it has survived 2,000 years in seawater, while modern concrete crumbles in decades. The precise formula was lost with the fall of the Roman Empire, its ingredients and mixing process buried by social upheaval. Or think of Greek fire, the legendary incendiary weapon of the Byzantine Empire, a naval terror so effective its composition was a state secret guarded on pain of death. When Constantinople finally fell, the secret died with its last custodians. These are not myths, they are historical case studies in technological amnesia. They prove that advanced knowledge can be extinguished, not by a lack of intelligence in future generations, but by the collapse of the specific social and cultural structures that nurtured it. In ancient Egypt, the most likely custodians of the granite working secrets were the priestly guilds and the royal workshops. Knowledge was power, and this kind of power would have been guarded with extreme secrecy. Imagine a master stoneworker, a man who knew the exact recipe for the cutting slurry, the precise tension for the saw, the ritual chant that may have accompanied the work. This knowledge was likely not written down in any manual we would recognize. It was an oral tradition, passed from master to a select apprentice through years of intimate training. The entire system was centralized, exclusive, and incredibly vulnerable. The technology lived in a fragile chain of human memory. Now consider the historical landscape of Egypt. Dynasties rose and fell. Religious revolutions occurred, like the dramatic shift to the worship of the Aten under Akhenaten, which upended the entire priestly establishment. Invasions and periods of social unrest were not uncommon. Any one of these upheavals could have broken the chain. If a ruling dynasty that patronized a specific school of craftsmen was overthrown, those artisans could have been scattered, their workshops abandoned. If a new religious orthodoxy deemed the old ways heretical or unnecessary, the knowledge could have been actively suppressed, its practitioners sidelined. The master craftsmen themselves, holding their secrets close to maintain their status and value, may have taken those secrets to their final resting places, believing the next generation unworthy or the world no longer in need of such wonders. There is also the possibility of a slower, more insidious fade. As cultural and spiritual priorities shifted after the Pyramid Age, the overwhelming drive to create these perfect granite vessels for the afterlife may have diminished. Grand projects became less frequent. The state's resources were directed elsewhere, without a constant, monumental demand pushing the boundaries of the craft. The cutting edge of the technology would have dulled through simple disuse. The most advanced techniques requiring immense resources and specialized teams would have become economically unsustainable. The knowledge wouldn't vanish in a day, but over generations, as apprentices learned only a simplified version of the craft, until the original, profound mastery became a half-remembered legend. This leads to a sobering thought. The technology may not have been lost in the sense of being misplaced. It may have been intentionally buried, or it may have simply withered away when the world that demanded it ceased to exist. We are left, then, not with a puzzle of forgotten machinery, but with a profound lesson about the ecology of innovation. True advancement requires more than a brilliant mind. It requires a stable society to support it, a cultural imperative to drive it, and a living chain of mentorship to carry it forward. When any one of those pillars falls, the edifice of knowledge can crumble back into the sand, leaving behind only its most durable artifacts to whisper of what once was possible. The conversation about lost technology inevitably brushes against a modern cultural phenomenon, the idea of ancient astronauts. This hypothesis, popularized in books and television, presents a straightforward answer to our granite mystery. Its premise is simple. The technological leaps we see in ancient Egypt are simply too great, too advanced to be the work of human hands alone. Therefore, the logic goes, this knowledge must have been a gift provided by intelligent visitors from another world who guided humanity's first steps into engineering. It is a narrative that captures the imagination by offering a clear, external source for the unexplained. On the surface, it seems to honor the artifacts by acknowledging their extraordinary nature. Yet a closer look reveals a deeper implication. This perspective, however unintentionally, can diminish the scope of human ingenuity. It suggests that our ancestors were not capable of such discovery on their own, that their creativity had a ceiling which only outside intervention could break. More critically, for all its popularity, the ancient astronaut theory operates largely in a space devoid of direct archaeological evidence. No star maps etched in granite clearly point to otherworldly instructors. No artifacts have been unearthed that can be conclusively identified as non-terrestrial technology. The theory often relies on interpreting mythology as literal history and gaps in our knowledge as proof of extraterrestrial presence. This is not to dismiss the curiosity that fuels it, but to examine its foundations. Perhaps the most productive way to view this idea is not as a historical claim, but as a cultural mirror. The very existence and persistence of the ancient aliens trope is a powerful symptom of just how profound our mystery truly is. It is a testament to the staggering achievement represented by a granite box or a drilled core, artifacts so perfectly made that they seem to defy the timeline we have written for ourselves. When faced with something that challenges our understanding of human history, the mind seeks an anchor. For some, that anchor is a narrative of divine or alien intervention because it resolves the cognitive dissonance instantly. It allows us to marvel at the object while comfortably maintaining our existing view of the ancient past. This framework shifts the conversation in a crucial way. Instead of debating the existence of visitors from the stars, we can ask a more grounded question. Why do we feel the need for such an explanation in the first place? What does it say about our own assumptions regarding the pace of innovation and the potential of cultures that left no written technical manuals? The alien theory, in the end, highlights the size of the gap in our knowledge, not what fills it. By acknowledging its cultural impact while scrutinizing its evidence, we gently steer the exploration back to where the physical clues lie, in the stone itself and in the boundless, often underestimated, capacity of the human mind to observe, experiment, and overcome. The real wonder may not be that aliens taught us to cut stone, but that we figured it out ourselves and then forgot how we did it. This tension between the stone's testimony and the official record places Egyptology at a fascinating crossroads. The field, built on meticulous excavation and peer-reviewed evidence, faces a legitimate paradigm challenge from the granite itself. Mainstream scholars rightly adhere to a principle of archaeological conservatism. Their position is clear: extraordinary claims require extraordinary evidence. To propose the existence of advanced machinery in ancient Egypt, one must produce archaeological proof of that machinery, parts, workshops, power sources, or at the very least unambiguous depictions in art or text. Since such direct evidence has not been found in a verifiable context, the consensus holds that the simpler explanation, using known tools with immense labor, must be correct. This is a foundational and responsible approach, a guardrail against speculation that could rewrite history on flimsy grounds. It ensures the discipline remains grounded in the artifacts we can actually touch and verify. Yet, the granite artifacts are the very things we can touch and verify, and their physical properties present a data point that does not fit neatly into the existing model. This creates a professional tension, a healthy friction that exists in any living science. On one side, established experts protect the integrity of the field from unfounded theories. On the other, independent researchers and engineers point to the tangible anomalies, arguing that the evidence in hand should compel a re-examination of the tools we assume were used. This is not a battle between fact and fantasy, but a debate over how to interpret stubborn facts. The core of the issue is the model of incremental, linear technological progress we instinctively apply to history. This model suggests humanity moved slowly from stone to copper to bronze to iron, with each step building logically on the last. The granite work seems to leapfrog steps, suggesting either a lost period of experimentation or a capability we have underestimated. When faced with such an outlier, the scientific impulse should not be to dismiss it to preserve the model, but to investigate it more thoroughly to refine the model. Some of the most profound breakthroughs in understanding come from studying the exceptions, the data points that do not fit. The danger lies not in new ideas, but in a rigid adherence to old ones that can inadvertently stifle curiosity. The questions raised by the drill cores and sarcophagi are not attacks on Egyptology. They are challenges born from the very material the field has dedicated itself to preserving. They remind us that history is not a closed book with all the answers neatly printed in the final chapter. It is an ongoing investigation where each new generation looks at the same evidence with fresh eyes and new tools. The silent precision of Egyptian granite is an invitation not to discard careful scholarship, but to expand the search for answers. It asks researchers to consider not just what tools have been found, but what combination of knowledge, material science, and applied physics could realistically account for the artifacts that sit before us in museum cases. This constructive tension ensures the story of our past remains alive, debated, and forever open to deeper discovery. The stone's silent testimony demands a new kind of conversation, one that transcends the boundaries of any single field of study. To solve a puzzle this ancient and complex, we cannot rely on archaeology alone or engineering alone. The most promising path forward lies in the deliberate fusion of disciplines, a collaborative effort where the language of science and the narrative of history finally speak to one another. This is not about replacing careful scholarship, but about empowering it with new tools and new questions. Imagine a dedicated research project where a geologist analyzes the microscopic composition of the powdered granite still trapped in ancient drill holes, identifying not just the stone, but the specific abrasive that cut it. Picture a mechanical engineer using computer modeling, calculating the exact torque and feed pressure required to produce the helical grooves on a core, revealing the minimum specifications of the machine that made them. Envision an archaeologist armed with these new specifications, returning to a known workshop site at Giza or Saqqara, no longer looking for a finished machine, but for subtle evidence of its footprint, like post holes for a heavy frame or wear patterns on stone benches that could have secured a vibrating saw. This interdisciplinary approach transforms vague speculation into testable, tangible hypotheses. Non-destructive technologies are key to this new chapter. High-resolution, three-dimensional laser scanning can create a perfect digital replica of a sarcophagus interior, allowing engineers to analyze tool mark patterns at a microscopic level from anywhere in the world. Advanced spectrographic analysis can examine the surface chemistry of a cut, searching for traces of binding agents or exotic abrasives that have long since worn away. This is detective work at the atomic scale, seeking clues our eyes could never see. The goal is to build a complete physical profile of the manufacturing process, reverse engineering it from the artifact outward. Each discipline holds a piece of the map. The historian provides cultural context, the timeline, and the site data. The materials scientist understands how granite fractures and wears under stress. The mechanical engineer comprehends forces, leverage, and energy transmission. Only when these perspectives are woven together can we hope to reconstruct the full picture. The lost technology may not be waiting in an undiscovered tomb. Its blueprint is far more likely to be found in the collaborative space between modern laboratories, in shared data sets, and in the willingness of experts to let the physical evidence guide them, even if it leads to unfamiliar conclusions. This fusion is how we move from wonder to understanding, turning the enduring mystery of Egyptian granite into a solvable equation written in stone, physics, and human ingenuity. The sound of a drill biting into granite was more than a workshop noise, it was a hymn. To understand the incredible effort expended, we must see it not as an industrial task but as a sacred act. For the ancient Egyptians, the universe began as a dark, watery chaos. The first act of creation was the emergence of a mound of dry land, a place of perfect order. Every time they took a raw, unshaped block of granite, they saw that primordial chaos, and every cut, every polish, every perfect right angle they imposed upon it was a reenactment of that first divine victory. They were not merely making a box, they were creating a pocket of eternal stability in a world of decay. The technology, therefore, was never just a means to an end. The precise feed of the drill, the unwavering straightness of the saw, the flawless finish, these were not benchmarks of efficiency, but measures of spiritual purity. A wobble in the cut was not a technical flaw, it was an intrusion of disorder. The craftsman at his lathe or saw was not a laborer, but a priest, using the physical laws of the world to manifest a spiritual ideal. His focus, his repetitive motion, the rhythmic sound of the work, all could have been a form of meditation, a way of aligning human action with cosmic principle. This philosophical lens resolves the apparent paradox of expending such monumental effort. The how of drilling granite was completely fused with the why. The perfection of the technique was demanded by the sacredness of the goal. You could not house a pharaoh's eternal spirit in a vessel that was anything less than geometrically perfect, because the afterlife itself was a realm of perfect order. The tool became an extension of this belief system, consecrated by its purpose. This perspective casts the loss of the technology in a new and poignant light. Perhaps it did not vanish because the recipes were forgotten or the machines broke. Perhaps it faded because the world that gave it meaning slowly changed. When the spiritual fire that demanded such perfect vessels began to dim, when cultural priorities shifted from eternal monuments to more immediate concerns, the overwhelming drive to achieve this specific, flawless result may have waned. The knowledge was not misplaced, it was orphaned. The most advanced techniques requiring a lifetime of devotional discipline would have no place in a society that no longer shared the foundational vision. The master craftsman's deepest knowledge was not just of abrasives and torque, but of how to translate faith into form. And when that faith transformed, the most profound levels of his craft became a language no one needed to speak anymore. The quarries of Aswan hold a monument to ambition and its limits. Here, still attached to the living bedrock, lies the Unfinished Obelisk. It is a colossal shaft of red granite, over 100 feet long and weighing more than 1,000 tons. It was meant to be a soaring needle of stone, but a catastrophic crack appeared during its extraction, and the project was abandoned. This apparent failure, however, is a treasure for understanding. It is a frozen moment, a snapshot of the quarrying process caught in time, offering clues no finished monument ever could. The obelisk's sides are a textbook of ancient engineering. You can see the precise channels cut by workers, trenches just wide enough for a person to stand in, dug straight down into the granite to free the monolith from the earth. Along the base, a series of drilled holes line up in rows. These are wedge slots. The method was likely to drive dry wooden wedges into these holes, then soak them with water. As the wood expanded with tremendous force, it would create a controlled fracture along a predetermined line, separating the obelisk from the quarry floor. This shows a profound understanding of material stress and fracture mechanics. Yet the final, fatal crack reveals the peril of working at this scale. Granite, for all its strength, is not a uniform material. It has veins, hidden fissures, and points of weakness invisible from the surface. The masters pushed their technology to its absolute edge, attempting to extract a stone of unprecedented size. They succeeded in carving it on 3 sides, but the granite itself, with a hidden flaw, ultimately said no. This is the humanizing lesson of the Unfinished Obelisk. It reminds us that these builders were not wielding magic or perfect alien technology. They were brilliant engineers and artisans working with a deep, hard-won knowledge of stone, but they were still subject to the material's whims. They calculated, they planned, they executed with stunning precision, but they also gambled, and sometimes the stone won. This artifact completes the picture. We see not only their triumphs in the polished sarcophagi and perfect drill cores, but also their struggles in this vast, cracked monument. It shows a technology advanced enough to conceive of a 1,000-ton obelisk, yet still vulnerable to the hidden realities of the natural world. They were not infallible, which makes their successes, the ones that did not crack, all the more remarkable. Their genius lay not in perfection, but in their relentless push against the very boundaries of the possible, learning from each fracture, each failure, to build the wonders that would endure. Precision on this scale demands more than muscle. It requires a reliable and steady source of power. The deep, consistent grooves in a granite core tell us the drill did not pause or waver. It maintained a relentless rotation under immense pressure. Human arms, no matter how many, tire and falter. Oxen cannot provide the rotary motion needed for such a task, so we are forced to ask what invisible force turned the spindle. The search for an answer leads us into the realm of mechanical advantage, where simple principles of physics are amplified by clever design. Consider the environment of the Nile Valley itself, a constant source of potential energy. Could they have harnessed the river's flow, large, undershot water wheels turning slowly but with tremendous torque could have been connected through a series of gears or ropes to a central workshop. The rotation would be steady, dictated by the current, providing the uninterrupted power needed to feed a drill into granite for hours on end. The sound of the river would become the heartbeat of the workshop. Wind, too, was a resource. While the simple sail captures wind for propulsion, more complex wind catchers or vertical sail mills could have translated that force into rotary motion. Imagine a large, framed sail structure on a pivot, catching the consistent northerly winds, its rotation transferred via a drive shaft to a cutting floor below ground. This is not about finding a fossilized engine, but recognizing a possible sophistication in energy conversion. Another possibility lies in the clever use of gravity and inertia. A heavy stone weight lifted by a team could be dropped to turn a capstan, storing that energy in a massive, spinning stone flywheel. Once set in motion, the flywheel's inertia would smooth out the irregular human effort, providing a constant, controllable rotation perfect for a drill or a saw blade. Pendulums, too, can be sources of rhythmic, amplified force. A large, weighted pendulum, once set swinging, could be linked to a ratchet mechanism, converting its back and forth motion into a one-way rotation. These are all technologies within the grasp of a culture that understood leverage and mass, requiring no mysterious fuels, only an intimate knowledge of physics. Then there is the more controversial artifact, the Baghdad Battery. Discovered in Mesopotamia and dating to a similar antiquity, it consists of a clay jar, a copper cylinder, and an iron rod. When filled with an acidic electrolyte like vinegar or grape juice, it produces a small electrical charge. While a single cell could not power a drill, a series of them could produce a notable current. The question is not whether they used it to light bulbs, but whether they understood the principle of electroplating. A steady, low-voltage current could have been used for the precise electroforming of tools or for depositing one metal onto another, a subtle technology that might have enhanced their material science. While evidence directly linking such cells to Egypt is absent, their existence in a neighboring culture hints that the exploration of basic electrochemical principles might have been part of the ancient world's hidden knowledge. The purpose of exploring these speculative sources is not to prove any one of them was used, but to highlight a crucial point. Precision machining does not exist in a vacuum. It sits at the center of a web of supporting technologies, a whole ecosystem of power generation, transmission, and control. The flawless granite artifact is the final product, but it implies a hidden infrastructure of thought and engineering that has completely vanished. The drills and saws themselves would have been the most durable part of this system, yet we cannot find them. How much more fragile, then, were the water wheels of wood, the rope drives, the leather bellows, or the woven sails that might have powered them? They would rot, burn, or erode to dust in centuries, leaving behind only the stones they were used to shape. This realization deepens the mystery exponentially. We are not searching for a single lost tool, but for the ghost of an entire industrial context, a whisper of an energy grid that once hummed along the Nile, turning human intention into enduring stone. Stories are the soft echo of a world's forgotten knowledge. When a technology vanishes, its memory does not always disappear. It often retreats into the realm of myth, disguised in the language of gods and magic. The ancient Egyptians left us more than stone. They left a library of stories, and within these tales, we might find the ghostly imprint of their lost engineering. Take the Eye of Horus, one of their most potent symbols. We see it as a mystical emblem of protection and royal power, but look closer at its design, the specific fractions that make up its parts. To the ancient mind, this was not just a sacred eye, it was also a system of measurement. Each segment of the eye represented a specific fraction, 1/2, 1/4, 1/8, and so on, all adding up to a unified whole. This was a mathematical tool disguised as divine iconography. It is a principle of division and precision, a concept absolutely vital to an architect dividing a massive stone block or an artisan ensuring the proportional perfection of a sarcophagus. The symbol may have been a teaching device, a way to encode the mathematics of harmony and scale into the very fabric of their spiritual life. Then there is the persistent legend of the Benben stone. Mythology says this sacred object, the primordial mound of creation, fell from the heavens. We often interpret this as a meteorite, a stone from the sky. But consider the metaphor from a technological perspective. What if a revolutionary new technique or material arrived so suddenly, with such transformative power, that it seemed to have a celestial origin? The introduction of a vastly superior abrasive, like diamond dust from a distant trade route, or the conceptual leap to a new form of tool, could have been so dramatic it was remembered as a gift from the gods themselves. The Benben was the seed from which the pyramid form grew, the capstone of perfection. This legend could be a cultural memory of a technological seed event, a breakthrough that made their grandest ambitions suddenly possible. We can even look beyond Egypt to stories that grapple with the nature of complex systems. The Greek legend of the ship of Theseus presents a profound philosophical puzzle. If every single plank of a ship is replaced over time, is it still the same ship? For a tradition of high-precision engineering, this is not an abstract riddle, it is a practical reality. Think of a master craftsman's lathe or drill, a machine essential to their work. Over decades, its parts would wear, its ropes would fray, its wooden frame would be repaired. The tool would be in a state of continuous renewal. The knowledge of how to maintain it, how to keep its precision true through every replacement part, was as vital as the original design. The ship of their technology could only sail across generations if the guilds understood how to preserve its function through constant, careful restoration. The legend captures the essential challenge of handing down a living technical tradition. These myths are not blueprints, and we must be careful not to read them literally. They are the cultural container, the narrative vessel in which a society carries its most important truths when the original context fades. When you cannot write down a complex engineering manual, you encode its principles into a story about a god's eye or a stone from the sky. The magic in the tale might be a metaphor for a forgotten physics, the divine power a symbol for harnessed energy. The stories become a mnemonic, a way to keep the essence of an idea alive long after the workshops have fallen silent. They preserve not the instruction, but the wonder, the sense that once we knew how to do something extraordinary. The granite sarcophagus is the hard evidence, but the myth is its lasting shadow, a reminder that some truths are too vast to be contained by fact alone, and so they live on as legend, waiting for us to understand the language in which they were written. The truth likely does not lie in any single dramatic answer. After walking through the quarries, examining the cores, and weighing every theory, a more subtle and human picture comes into focus. It is a picture of synergy where several advanced but plausible technologies worked in concert, driven by a culture with a unique and powerful vision. The most credible explanation is not a magical tool or an alien blueprint, but a sophisticated system, a lost engineering ecosystem that combined material science, mechanical genius, and spiritual purpose. Imagine not a single machine, but an integrated workshop. At its heart is a drill rig of elegant design. It is not powered by electricity, but by the coordinated pull of oxen or teams of men turning a large capstan. This rotational force is transferred through a series of wooden gears or a clever rope drive, not to spin the drill wildly fast, but to generate immense, unwavering torque. The drill shaft itself is heavy and perfectly balanced, suspended in a sturdy wooden frame to eliminate wobble. This is the mechanical arm, providing the steady, relentless pressure the granite cores demand. But the arm needs a hand. That hand is the cutting head. Here, the secret is in the abrasive. It is not common sand, but a carefully processed powder, perhaps of crushed emery or even sourced diamond fragments, mixed with water into a precise slurry. This super abrasive is fed continuously into the cut. The heavy, stable drill shaft rotates, pressing the copper or even stone-cutting head into the granite, while the diamond-hard particles in the slurry do the actual cutting, grain by microscopic grain. The perfect balance of the machine ensures the feed rate is constant, creating those uniform spiral grooves. The superior abrasive ensures the cut is clean and efficient, not a chaotic grind. This combination explains the evidence beautifully. The machine provides the consistent force and motion. The advanced abrasive provides the cutting efficiency. Together, they achieve what neither could do alone. Yet this physical system is guided by an invisible one, a master geometry. The artisans use water levels for flatness, 3, 4, 5 chord knots for perfect angles, and astronomical alignments for orientation. Every cut is first a line in a sacred diagram, a mathematical prayer made solid. The religious imperative for perfection ensures no shortcut is taken, driving the refinement of the entire process over generations. This synthesis feels both advanced and authentically human. It does not require impossible power sources, only a profound understanding of leverage, balance, and materials. It turns the mystery from a search for a single fantastical device into an appreciation for a lost industrial culture. This was a system, and like all complex systems, it was fragile. Its knowledge lived in specialized guilds, its techniques honed for one supreme purpose, creating eternal vessels of order. When social structures shifted, when the demand for such perfect monuments faded, the delicate chain of apprenticeship broke. The machines made of wood and rope rotted away. The secret recipes for the abrasive were forgotten. The geometric rituals lost their practical meaning. What remained were the indestructible products, the granite boxes and drilled cores, silent monuments to a synergy of mind, material, and faith that the world would not see again for thousands of years. Those drill holes in Egyptian granite are more than historical curiosities. They are portals into a past that is more sophisticated and mysterious than we often allow ourselves to assume. Our journey has taken us from the silent testimony of the Petrie cores to the overwhelming scale of the Serapeum boxes, from the humble copper chisel to the resonant possibilities of sound. We have circled a central enigma, the ghost of a technology seemingly erased from the timeline of human achievement. This exploration does more than challenge a textbook. It challenges our very perception of history itself. We tend to view the past as a linear march, a steady climb from simple to complex, from primitive to advanced. But the evidence carved in granite suggests a different story, one of peaks and valleys, of brilliant plateaus of knowledge that were reached, inhabited for a time, and then lost to the long erosion of centuries. The true value of this enduring mystery may not lie in uncovering a single, definitive answer. It may reside instead in the profound questions it forces us to ask. What is the true ceiling of human ingenuity when driven by a powerful cultural vision? How fragile is the chain that links one generation's mastery to the next, and what other chapters of our own story have faded into silence, leaving behind only the most durable fragments for us to ponder? The stones of Egypt do not give up their secrets easily, but they have given us a gift, a permanent puzzle that stretches our imagination and humbles our assumptions. They remind us that the narrative of progress is not a straight line, but a complex, often interrupted dialogue between human ambition and the materials of the world. If you found this journey into the heart of an ancient mystery compelling, consider subscribing for more explorations into history's greatest unanswered questions. We would love to hear your thoughts, so let us know in the comments below which explanation for this lost technology resonates most with you.